next, Sanay Dev, senior software developer from Amazon, will share how Amazon scales its payment stack to handle millions of requests seamlessly. Please give it up for Sanay, folks.
Hey, good afternoon. I'm so glad to be here. Thank you everybody for joining. I'm Sanay. I'm a senior software engineer with Amazon. I've been there with Amazon for 4 years building ultimately complex distributed systems on the cloud. Today I'm going to present my learnings while building these systems and keeping them reliably resilient. So today, since this is a lightning talk, I don't think I have enough time to get into all the topics. What I'll try to do is I'll try to cover a breadth of those so that you can go back with some unanswered questions, a lot of curiosity, and you can hit me on LinkedIn or you can reach out to me in Hall 1 or Hall 2 if you have any questions. So I'm going to talk about how Amazon Payment Services scale for approximately 20 million requests on a daily basis. There are times when it handles more than 100 million requests per day. So a quick show of hands, how many people have shopped on Amazon? Raise your hands. How many people have shopped during a sale? Okay. A lot of people trying to make our lives difficult. Anybody wants to guess? I don't think guesses are allowed. So what you see there is a tweet from Werner Vogels. He's the current CTO of Amazon. And this is a graph representing the microservice architecture of Amazon. And it shows all the systems that are required to power the shopping on Amazon. And this graph is back from 2008. Now I think it should be 4 folds now. So this is the level, and so I'm trying to put everything to perspective. So these are the systems that work together to bring a sale, and Amazon Payments, at least I can guarantee, has never gone down in the last 3-4 years. So I want to expand by trying to make you understand what a sale is. So there are 2 broad categories of sales in Amazon. So sales could be, there are multiple categories, but precisely there are 2 broad categories. One is a flash sale and one is a plan sale. So flash sales, so the one that you see there, they are sales like Xiaomi or RedMI sales, where the traffic spikes from around 4,000, 5,000 to 15,000. These are just representative numbers. There is a spike of, what I'm trying to say is there is a spike of more than 15 or 16 times within minutes, and it goes down in around 1 hour or so. On the contrary, there are planned sales where the traffic stays up for more than 30 days. So you would have recently seen the Great Indian Festival sale that went on through entire of October. Both these sales present their own set of challenges. There are systems that are involved, and they work differently during both the sales. And I'm going to present to you today on what it takes to keep these sales resilient. How do we keep them working correctly? So with any distributed system, the most simple philosophy is, and the best part is, you can always scale up to solve the problem. So let's say if one instance cannot do your job correctly, what you do is you scale it. You put more money at the problem, right? But simply scaling up is not the solution, and it's not a simple solution. So there are two ways to think about it. Think of it when you know how much traffic you're going to get, which is almost never the case. Never the case, because even when you plan, let's say you have an inventory of 5,000 mobiles, you could have 1 lakh users, you could have 10 lakh users, you could have only 10,000 users. So you can never plan. And you could ask me, why not just auto scale? Why not put the new infrastructure which scales up? Auto scaling has a lot of challenges. Auto scaling has, you need availability. For example, you request AWS for resources, but they don't have resources at hand. Even if you have a resource, scaling up or starting the server will take a lot of time. So when you're talking about millions of dollars per minute, you don't want to go down. You don't want your server to go down. And there was an outage back in 2020 where 30 minutes of a downtime cost us around multiple millions in revenue. So how do you solve the problem? So what I'm going to tell you is a broad scheme of things on how different tech companies try to solve this problem. How do they try to tackle it? So the broad categories are demand forecasting, performance testing, traffic shaping, dependency production, and redundancy. I'll go over them in detail a little bit later. The most interesting one is demand forecasting. So let's say you have a shop or you have anywhere where you want to supply something to a customer. What is the first thing that you would want to do? You would want to predict the number of customers that are going to come to you, right? So Amazon specifically has a very complicated architecture of forecasting the traffic that comes there. When you talk about sales every day, there are sales going on every day. There are flash sales going on. There are long planned sales going on. So you forecast, let's say, there are going to be 16,000 requests per second, and your server could handle, let's say, 200 requests per second. I'm talking about one server. So what you would think is you just need 80 machines that could, or 80 servers that could solve your problem, but that's not always the case because, and we'll talk about why a little later. The primary reason I was talking about why you can't just think of estimating the expected traffic and just put more resources to it. That's because, first of all, forecasting is an estimate. It's never correct. So you always plan. And then you don't know the performance of your servers accurately. So let's say there is a server which can handle 16,000 requests, but the nature of the requests were different. So things start to perform differently in times of peak stress. So if your CPU is at 60% utilization, you would think that it would be able to, I mean, it scales linearly, but it doesn't. So there are multiple factors that come into play, CPU and memory and disk and heap. So what companies try to do is, what at least Amazon tries to do is, it tries to test every server by stressing it beyond limits. So how do we stress it is, we try to mock unprecedented scenarios. So you could think of unexpected traffic spikes. You could think of latency degradations in multiple systems. You could think of services going down. So let's say I'm a payment system and I'm talking to a different payment partner and the payment partner goes down. So we mock those scenarios and we subject our servers to those situations and we see how they behave. We perform analysis and then we react. So for example, if we know that when the traffic spikes by 5 folds within a minute, we know our CPU browns out. So what we would do is we would always keep that buffer. We would keep monitoring it during a sale or something. So this is a typical graph of what a performance testing looks like. The blue line that you see is the incoming traffic that you are trying to stress it with. So you'll see there are flat lines. This is a staircase-like pattern. So you give it some requests. So you give it, like, for example, 200 requests, and you wait for some time to see how many requests are failing, how many are succeeding, and you have a threshold, which is shown by the brown line there. So that tells you that whenever X number of failures, X percentage of failures start happening, you would want to shut down your stress test. You would then take that as your safety TPS or safety limit, and then that's what you'll use to estimate how many servers or how many instances of the server you need. One very interesting thing is traffic shaping. So as I told you, you are not in control of what request comes to you. What you are in control of is how you allow them to come to you. For example, let's say you were planning for 16,000 requests, but you suddenly see that there are 18,000 or 20,000 requests coming in. So you could do a lot of things to solve that problem. What you could do is, you could start dropping all the requests after 16,000. You could do some sort of a prioritization where you could think about these are high value clients and we don't want to drop their request. We will drop somebody else's request. So you do intelligent load shedding or something like that. You do rate limiting. For example, there are multiple clients that are accessing your service. What you could do is you could give them limits. So if you hit me with more than 500 TPS, I'm going to discard all your requests. So you are very balanced with all your clients. You also have customer-based limits where you don't allow a customer to hit you more than, let's say, 50 times a minute or something. So the most interesting part of load shedding is traffic shaping is load shedding. So this is a typical service graph where you see if you increase the request count, below is the TPS and on the left is the response time. So if your TPS increases normally, you'll see that there's not a lot of lag in the response time, but it suddenly starts to spike beyond a certain limit where your service starts to degrade. So that's a typical graph of how a service performs. And this is how availability plays if you don't have load shedding built in. So the red line, as soon as your timeouts pass through that threshold, your availability suddenly drops to 0. So you are not able to serve any of the requests that are coming to you. What you instead want to do is, you don't want your availability to go down to 0. You want to still serve some people who are coming to your platform. So what you instead do is, you, beyond a certain point, you see the green line, that's the availability. The blue line on the horizontal line at the top, the dark blue one, shows the availability of the requests that your server is still serving. And the red one is the response time of the requests that are being served. So instead, if you start shedding load based on, let's say, prioritization, that this request is a high value request, we don't want to shed it, and you instead start shedding some more requests, your availability does not drop so strongly. One more important thing is dependency protection. I think a lot of speakers before me told you how dependencies are important. So for example, in a payment system, there are a lot of dependencies. There are people calling, there are upstream dependencies and then there are downstream dependencies. So for example, if I am a payment selection page, I have processors that I'll call for payment processing, and then I would probably have an OTP page that's giving me OTP. So what you would want to do is, if you've seen that you're getting more traffic than what you've expected, you wouldn't want to overburden your clients. You would know that, okay, I can't serve this request, so you don't call your downstream for that. And you protect your downstream with all your might, because what has happened previously in Amazon, as I've seen it, is dependencies did not take care of their downstream dependencies, and they kept retrying it with what we call a retry storm. So you keep pinging it that give me a request, and the downstream browns out. It says I can't, and then instead of you, it's not just you who are affected. I think a lot of other downstreams get affected. It causes a lot of problems, so you instead want to protect your dependencies. This is a very broad topic. I would want you to deep dive later. Important things to note being client timeouts and circuit breakers. So circuit breaker is a separate topic in itself. Client timeouts are good ways to control how you let your dependencies be taken care of. One thing that I've learned the hard way, despite all the literature talking about it so much, is you need to build in redundancy. I think the primary problem is we think of redundancy in forms of data only. We think data needs to be redundant, but in a system as complicated as Amazon, what you need to build is you need to build redundancy of all sorts of systems. So if your bank or payment processor is down, what you need to do is you need to have a alternate bank. I think everybody would have heard the scenario with PhonePe where their processing bank failed and they had to migrate it overnight and pull all-nighters. So you don't want that happening. So if you have a database, you would want your database to have more replicas. You want to have them redundant data sources. If you have a dependency, for example, if somebody sends you an OTP, if that's the downstream that you need, you should have multiple partners. You should have multiple systems that do the job for you. So baking in redundancy is a very important thing when you are serving so many requests, and everything is important because there's a lot of money that's involved with payments. So when you've done all this, so the major key thing to learn after you've done something is to retrospect, because if you don't learn from your mistakes, you're setting yourself up for failure. So you need to retrospect what went well, what went wrong. What helps is we most of the times take snapshots of all the metrics, all the dashboards that are there, so that the next time that you are predicting that what happens in 16K requests or 70K requests, you know how it behaved the last time. You have something to refer to, and you learn from it. You also need to record what went well, because not knowing what was going well all this time could land you in trouble, because the next time you don't know what broke because you're not probably looking at it. Once you've done all this analysis, I think in Amazon we spend a lot of time doing it after the primary sale events, which is Diwali and flash sales, which happen all the time. We look into our dashboards and we prioritize a set of backlog items, and we think solving what would give us the maximum output. We prioritize them, we fix them, and we wait for the next sale to happen. That's all from my side. You can reach out to me later if you have questions. Thank you so much. Thank you so much for being a patient audience.
Audience, do we have any questions for Sanay? Yes, please.
Are we taking questions? We are taking questions?
Hey, hi Sanay. Here.
Hi.
I'm Vishaka. So I have total 5+ years of experience as a software developer.
Mhm.
So my question is more on the like the graph that you have shown, where the availability. Sorry, when we start, when our API starts giving out, let's say 500 exceptions, it can drop to it can drop to a point zero, the availability of our application. But if we start accepting requests with the higher priority, we can we can make sure that it won't drop the availability to zero. What I want to understand, what are and let's take an example for a API as a REST API, and I just want to understand how are those prioritization done? What criteria are chosen to prioritize the request, and how is that basically implemented? If you can just shed some light.
I think that's a good question. It's a very subjective thing on how you want to prioritize it. With Amazon, we have our payment selection pages or payment processing pages have clients that talk to us. So you know the business value. So you know if somebody is trying to do a mobile recharge versus somebody who's trying to purchase a air conditioner, you know the value is going to be higher on purchasing that air conditioner. So you know the clients, you know everyone who, you know the value proposition. So at that time, you stop taking requests for mobile recharges. We don't typically do it so simply. I think no business does it so simply. We prioritize. That was one example of how we do it. There are things. So for example, there are requests you know are going to cost you so much on your CPU. For example, let's say your payment processing is coming from a client that demands a lot of computing power, and you see that your CPU is going down. So there are very complicated systems that are at play in Amazon. So you have static rules that you can use, for example the client one that I told you, and there are dynamic rules that you can use. So you could use that this resource will require a lot of CPU. I'm not going to serve this right now because my CPU is blocked. There are some which require a lot of memory because they need to talk to a database, they need to pull something into the cache. So that's how you do it. And you also do sorts of prioritization with your features. For example, let's say you don't want customers to do two-factor authentication when your OTP service is down, right? So you start killing those features. So that's also one sort of prioritization. You kill features, you kill downstream calls. Does that answer?
Yeah, that does. Thank you.
Any more questions?
All right then. Thank you for your remarkable insights, Sanay.
Thank you.
Now, I invite Kadirvel Vanyarajan, Vice President of Engineering, Motok, to felicitate Sanay with a token of appreciation.